This program is presented by University of California Television. Like what you learn? Help others discover UCTV podcasts by leaving a comment or rating for us in iTunes. Also, make sure to check out and subscribe to our YouTube original channel, UCTV Prime, available only on YouTube. This UCTV podcast is sponsored in part by Audible.com, your destination for the widest selection of digital audiobooks available, including many by guests you've seen on UCTV. Audible.com is offering UCTV viewers a free 30-day trial subscription and one free audiobook download. Just visit audibletrial.com/UCTV to sign up. And thanks.
So, as Charlie said, this work really grew out of the year I spent at the State Department, where I worked with the diplomats who negotiate climate agreements for the United States, and I also served as the science advisor for Todd Stern. And those two things in that year in Washington really changed my perspective on climate change. When I came in, I was a natural scientist who'd thought about these issues for 20 years, but never really had much of an opening into the policy. When I left after that year, I had at least some grasp on the challenges that policy poses to progress on climate change. And I've tried to integrate those two backgrounds in the story I'm going to tell you today. So first I want to just take a minute to tell you about what I have done for most of my career. Most of my career has been spent reconstructing climate change in the past, specifically on geological timescales. This is one example of how we do this. This is a cruise we went on in 2009 off the Galapagos Islands. And this is actually how we take cores from the bottom of the ocean. Basically, you punch a PVC pipe into the ocean floor. You get a column of sediment, and in that sediment are various kinds of signals that tell you about climate history. In this case, we were studying the history of the climate of the tropics, and we were specifically after the shells of these planktonic organisms that float around the ocean and basically record in their chemical composition aspects of ocean history. Now, there's a specific aspect they record that I was one of the folks who made a key discovery in that area, and that is we found out that the magnesium content of these shells records the temperature of past ocean waters. And that discovery, which was about a decade ago, enabled us to make a series of reconstructions, especially in the tropics, about climate history that got me quite interested in the whole question of temperature evolution, both in the past, the present, and the future. And I'm not going to talk about the past today, it's a different subject, but that's really what led me into the work I want to, that led me to the State Department, I should say, first. So as Charlie said, in 2010, 2011, I was able to be a Jefferson Science Fellow at the State Department. This is the only time I met the secretary, frankly. It was just for a photo op. But I was very impressed by her. But anyway, 12 of us came to the State Department and worked in various bureaus in state. We had to get top secret clearance. It was a very, very different experience than being a professor at UCSB. For one, I had to buy nicer clothes. But again, the perspective I got there on this problem of climate change, I think, was invaluable. Okay, so let me start right in with the question that I want to address today. So Todd Stern is the special envoy on climate change at the State Department and for this administration. He was appointed by Barack Obama, President Obama, and Secretary Clinton at the beginning of the president's term. And a special envoy basically has a role that supersedes the normal diplomats and bureaucrats that work at the State Department. In a sense, they have a direct line to the president's thinking and can cut through some of the lower level negotiation issues that sometimes hold up progress. So, Todd is a pretty formidable guy. He's a lawyer by training, extremely well-spoken, extremely well thought of, I think, in DC. And my interaction with him was often, frankly, by email, sometimes just on my BlackBerry. But in March of 2011, Todd sent me an email and he said, this article had just appeared, and that's this one, right, that I've put on the PowerPoint slide. And I wonder if you could look into this question of whether a 1.5 degree or 2 degree temperature limit for global warming is feasible. And this was the article that prompted the question. This is Cristina Figueres, who is head of the UNFCCC, and she basically made this statement that we shouldn't just look at 2 degrees. It says here, I don't know if I can quite read it, 2 degrees is not enough. We should be thinking of 1.5 degrees. If we are not headed to 1.5 degrees, we are in big, big trouble. Well, that statement got some hackles up in the State Department because the US negotiating team and the president had spent a lot of time specifically negotiating this 2 degree limit as part of the Copenhagen Accord, which was basically December 2009, and then in Cancun was basically agreed to. And so when Ms. Figueres basically came out and said, well, maybe we should think about 1.5 degrees, the reaction was not so positive. But the scientific question of whether we can do either of these targets is a really, really interesting one. And the way Todd posed the question to me was, first of all, can we do it? And second of all, is this the right limit? Why not 3 degrees? Why not 4 degrees? What's the right number? So I spent about a month working on this. Typically the way things work in the US government is it's a fast turnaround. Typically you get a request in the afternoon and they want the talking points the next morning. In this case, I was given enough time to do a good job, and it was probably the most interesting thing I did there. And so this talk is an outgrowth of that work. Okay, so to answer the question, the first thing you need to do is look at the actual place where the 2 degree limit comes from. Well, this is the actual draft decision from December 2009 of the Framework Convention on Climate Change, known as the UNFCCC. And you can see that this text, which was, by the way, partly written by the president, or at least with the help of the president, it states very clearly that we shall recognizing the scientific view that the increase in global temperature should be below 2 degrees Celsius. Now, it's a very interesting question as to where that 2 degree number comes from. And it's a little bit beyond the scope of the talk, but it actually goes back to some work or some ideas Bill Nordhaus of Yale University advanced in the 70s. And then it kind of generally became adopted by the German government in the 90s. And so that's really where the 2 degree limit comes from. I'll tell you more about whether it's the right number. That'll be the first part of the talk. But that's what ended up in the Copenhagen Accord. There was also this 12th item in the Accord, which says that as the science advances, we should reconsider whether 2 degrees is the right limit. Perhaps we should consider 1.5 degrees. So Ms. Figueres in her statement was actually justified, I guess, by that point number 12. Okay, so as I said, there are 2 parts to this question. I want to address both of them. I'll start with the first, which is why 2 degrees Celsius? Is this the right choice? And then the second part of my talk will look at the question of feasibility. Okay, so there are different ways to frame this question of the 2 degree temperature rise. An obvious thing to think about is the impacts of global temperature rise. How will the Earth change if temperatures rise by 2 degrees? And how will that affect different systems on the Earth? A second way to look at it is the question of tipping points. Tipping points are recognized as parts of the Earth system that if they get beyond a certain threshold, they're going to move very rapidly to a different state. And that's what probably the one I think is one of the strongest arguments for establishing a temperature limit, although I'm not convinced necessarily 2 degrees is the right number. A third way to look at this is the impacts on extreme events. Obviously, extreme events probably are the ones that have, well, I'd say along with tipping points, are the ones that probably would have the greatest human impact. We think about floods, hurricanes, storms, droughts. Whatever you might consider, obviously, if some of those extreme events would be known to accelerate above a certain temperature limit, that would be a good rationale for thinking about trying to limit warming to that temperature. And finally, one that I think hasn't been considered before, but I think is a very strong candidate, is the question of ocean acidification. So I'm going to go through these 4, and then I'll get to the question of feasibility in the second part of the talk. Now, this is a really famous chart that's become euphemistically to be known as the burning embers chart. It was featured in the 3rd assessment report of the IPCC. The IPCC is the Intergovernmental Panel on Climate Change. Roughly every 7 years, they release a comprehensive, very carefully authored report about all aspects of both physical, social, and economic issues related to climate change. I believe Charlie is a lead author on the IPCC report. And in that 3rd assessment report, which I believe was 2001 or 2000, there was this famous chart that came to be known as the burning embers chart. And the idea behind it, charts have a lot of power, right? There's words, but then what typically happens with these, if you pick up these assessment reports, they're bigger than phone books used to be. And let's face it, most people don't read them. So what they do is they basically extract some of the text and some of the key figures into what are called summaries for policymakers. And those are the things that tend to have the biggest impact. Actually, one of my roles at the State Department was to work and approve the summary for policymakers associated with the Extreme Events Report, which was just released this year. This is one of those charts that ended up having an outsized impact. And the real reason is people thought of each of these columns as representing burning embers that got gradually hotter or worse for our planet or our society, either way you want to think about it, in association with temperature rise. And I don't know, for me it's a little hard to read from the side. Hopefully for you can see these numbers. But they go from a scale of 0, 1, 2, 3, 4, 5 degrees. And here's the part as of this time that had already been experienced, about a 0.6 of a degree warming. So I've placed this line just to show where a 2 degree warming would actually occur. Okay, so the divisions basically are, the first column represents risks to many. The second column represents, I'm sorry, I read that wrong, excuse me. Risks to unique and threatened systems. I'm going to read off this because it's going to be easier. Risks of extreme weather events. Distribution of impacts, aggregate impacts, and risks of large-scale discontinuities. These would be like tipping points. And you can see some examples of each of these 5 categories. For example, loss of unique and threatened systems, such as coral reefs, tropical glaciers. Increase in extreme events would be number 2. Number 3 would be some regions or countries face greater harm than others. 4 would be impacts distributed across the globe, such as economic impacts. And finally, these are the tipping points, which I'll have more discussion about. Now, when you look at this slide, if you just accept the graphics that whoever made the slide, and Steve Schneider at Stanford had, I think, a strong influence on this slide, place those red bars properly. I mean, if you didn't know much, you might just say, geez, I'm not even sure 2 degrees is going to be right, because maybe we should put this line somewhere down here, because we don't want to get into the red area on any of these 5 things. We don't want to lose coral reefs, for example. But of course, the judgment call about where to place the red is very much a subjective judgment. So what I wanted to do was look a little bit more deeply into this question of whether that 2 degree placement is the appropriate one. Now, a guy named Tim Linton, who's a British scientist, has, along with Hans Schnellhuber, who's a German physicist interested in this question, has done a lot of work looking at this question of tipping points. I can't tell, can folks actually read what's written on the slide? Okay, that makes it more challenging. So I'll try to read this out, but you can hopefully get the basic idea. So what this illustrates is tipping points that you could postulate might be responsive to specific global temperature rises. Some of these will probably be very familiar to you if you've seen Al Gore's An Inconvenient Truth, or if you followed any of the popular media on climate change. So here's the Greenland ice sheet. That's an obvious one that there's concern about. Here's the West Antarctic ice sheet. That's the more vulnerable part of Antarctica. Here are those tropical coral reefs I just made reference to. This is one that received a lot of attention about a decade ago, the Atlantic Thermal Haline Circulation. You might have seen the movie, and it's dropped out of my memory. The Day After Tomorrow, thank you so much. You might have seen the movie The Day After Tomorrow that postulates that this could change overnight and we're all going to be covered in a wall of ice, or at least those of us who live in the Northeast. Not very likely, but there was this kind of paradigm that was quite popular about 10 years ago that this could really rapidly shift, that it could be a tipping point. I would say that's something that's maybe less in vogue these days. So here are the ones that I picked out for Todd that I thought had the greatest likelihood to be sensitive to this specific question of a threshold temperature that could trigger a tipping point. So I put in that category, and again, these are my subjective judgments, partly on my reading of the literature, partly, and I would say in large part on 2.5 decades of work in the paleoclimate arena, where many of these, our understanding of many of these tipping points comes from, because many of them have quite long time scales that can only be evaluated through geological data. So the Greenland ice sheet is an obvious one. Amazon rainforest dieback, that's a particularly good one because we have some indications from 2 very large droughts that happened within the last decade that there could be a big impact in how much carbon is being taken up in the Amazon. And that gets into the question of carbon cycle feedbacks, which I'll touch on in the second half of the talk. West Antarctica, we put very much in a category with Greenland. Permafrost is another one there's been a lot of discussion on, whether you're discussing release of carbon or methane. That's again an example of a carbon cycle feedback. And tropical coral reefs, I think, is another one that really makes it harder not to be able to see it, but we'll do the best we can. Tropical coral reefs are something that there's pretty clear evidence right now are really suffering a degradation. Now, what's causing that degradation is a combination of rising sea surface temperatures, increases in ocean acidification, and also fishing pressures and other environmental degradation. So it's a little bit hard to separate out, but those are the ones I thought would be good candidates to think about in terms of threshold temperatures. So the next question would be, is 2 degrees the right number? I think it's really hard to say. I think something in the neighborhood of 1.5 to 4 degrees is probably the triggering point for most of these thresholds, but I had a really hard time nailing down which one would correspond exactly. Obviously, if this were an easy problem to solve, right, we would just say, hey, let's just keep it below 1.5 degrees so we don't have to worry about it. But that's not the framing of the problem, as you're going to see later on. Okay, so let's move to extreme events. Obviously, extreme events are probably where society is most aware of climate change. People pay attention when you have 100 days of 100-degree temperatures in Texas. People pay attention when you have droughts that wither crops, whether they're due to global warming or not. So that's something that obviously has to be looked at in terms of its sensitivity to global temperature rise. Now, the IPCC, fortunately, released an assessment report called the SREX, the Report on Extreme Events, this past year. And again, as I said, at the State Department, I was on the government review team for that. I worked with other distinguished scientists reviewing the text and sending in questions to the IPCC. And I also was at the plenary in Abu Dhabi, where we looked at and approved the summary for policymakers. And what I'd like to say to you is that this is a really good report. It's really well done. The IPCC has been criticized on some other grounds, but in this case, I think it's just really authoritative, it's conservative, it's careful, it's backed by the best science. So what I did is I just extracted some of the major points where you can see a distinct relationship between extreme events and temperature rise. So there will be a substantial increase in all of these things are preceded by the statement, as temperatures rise. There will be a substantial increase in warm temperature extremes. Okay, that's not a big surprise. Maybe we're having that today. It is late October. It's a bit toasty out there. The frequency of heavy precipitation over many areas of the globe will increase. Basically, warm air contains more water vapor. That, in turn, gives rise to heavier rainfall. And therefore, you can predict theoretically and also empirically that the frequency of heavy precipitation events will increase, and that would, one would think, lead to greater incidences of flooding. Average tropical cyclone maximum wind speed is likely to increase. It's not a very large increase, and actually the frequency of events either stays the same or decreases, so I'm not sure that's a major one. The fourth point, droughts will intensify in some seasons and areas. You know, again, it's not real satisfying, but that's what the conclusion of the report was. One of the places was the Southwest United States, another place the Mediterranean. But in other places, it was much hard either to pull a signature out of the past or to make a prediction for the future. Mean sea level rise will continue to upward trends in extreme coastal high water. Sea level is rising 3 millimeters per year, so that makes sense. And finally, changes in heat waves, glacial retreat, and/or permafrost degradation will affect high mountain phenomena. Okay, so those things, again, you know, like the tipping points, they sound like things we want to be aware of, but it's difficult to establish a cutoff temperature above which extreme events accelerate. Again, you know, the question we'd like to know is, at what point do these things become intolerable in terms of our ability to adapt to those changes? And my reading of the literature, and particularly of the SREX report, is it's really hard to say what that discrete temperature limit is, other than to say for sure that as we go to warmer temperatures, we're going to have to adapt to a greater degree to such extreme events. Okay, the last category I'd like to touch on to the question of the temperature limit we'd like to aim for is one that's a little bit more satisfying, because we can really scientifically nail down what the number is. And again, I think it's really worth, you know, noting this one, because it's not one you hear you hear about ocean acidification, but you don't hear about it concatenated with the question of global temperature rise. Now, Mike Eby and his co-workers, particularly Dave Archer and Andy Weaver, put out a very nice paper in Journal of Climate a few years ago, just 2009, where what they did is they ran a model and basically looked at the linked question of ocean acidification and global temperature rise. And you know, it's probably going to be a little hard to see the charts, but I'll just give you the basic message. What these show are the pH anomaly for particular injections of total carbon. And I'm going to get to this point about cumulative carbon just in the second half of the talk very shortly. But for now, I'm just going to say, if we release cumulatively a teraton of carbon, that's 1 trillion tons of carbon, that would correspond to a temperature rise of about 1.5 to 2 degrees Celsius. I'll show you the justification for that in a minute. But what that does to surface pH is it reduces it by less than 0.2 of a unit. Now, the ocean's pH is slightly alkaline. Before we started our grand experiment of burning fossil fuels, surface ocean pH averaged about 8.1 to 8.2. Today, it's about 8. So it's dropped about 1/10 of a unit. If we can keep within that 2-degree temperature limit, now you can see how these two problems are linked, then we could actually only see a change of less than 0.2. Now you might say, 0.2, you know, do we really want to go there? Well, we're probably going to go there anyway. My judgment, and talking to experts, having worked a bit with calcifying organisms myself, is that probably most marine organisms could withstand a change of about 0.2. The place we don't want to go is the 2.5 teraton release. So that's about obviously 2.5 times this. As you're going to see in a minute, that gives you a temperature rise of about 3 to 4 degrees. That reduces surface ocean pH by 0.4 units. There is no question that for calcifying organisms, which are an important part of the ocean biota, that will have a huge impact. And just to underscore that point, this is a comparison of a gastropod living in the Adriatic in a region that is not subject to high CO2 or low pH. And it turns out in this region there are natural volcanic CO2 vents that acidify waters, and you can see the tremendous difference. All these calcifying organisms basically are swept or basically dissolved off of shells that come from those lower pH environments. So I would say, if we go here, 2.5 teratons, we're looking at a very, very different ocean. And that's something, and again, I like this one because as a scientist, I want to actually find a number. I can tell a policymaker, we don't want to go we don't want to go beyond that point. And I think ocean acidification is a really good candidate for that. Okay, so that is the first part of the talk. And I'm going to now segue to the question of feasibility.
Dave, can I ask you a question? All of the quotes on temperature are presented. Are they pre-industrial by the
Yes, sorry, they are 2 degrees relative to pre-industrial.
All right, so we're at 0.6.
We're actually a little higher now. We're like 0.76, 0.8. Good point. Thank you. Okay, so the second part of my talk, which although I'm not an economist and we have a real one sitting in the audience, really captured my imagination. I probably spent more on this, although it's less akin to my background, was the question of can we actually do this? Are the economics, is the policy, is the diplomacy such that we could actually achieve a 2-degree temperature limit? So the way I'm going to lay this out, the question of feasibility, is I want to look at there's really 4 major parts of this that I'm going to look at. Projected warming depends on a number of different things, as you could well imagine. But these are the big ones. How much we've emitted so far. How much we're going to emit in the future, right? No surprise there. What are the carbon cycle feedbacks? Now, this is one that wouldn't necessarily seem obvious, but if we emit carbon and that warms the planet such that more carbon is emitted, that's a feedback that's going to enhance what we're adding. So that's something that we have to take into account. Climate sensitivity is probably the single biggest factor aside from the emission pathways. It is basically an aggregate assessment of how the climate system responds to a specific forcing in the form of an energy perturbation. In this case, we're interested in the fact that we're putting more greenhouse gases in the atmosphere. And finally, there's a wild card that's very important, which is the current and future strength of aerosols. These are the pollutants that are added to the atmosphere, mainly in the form of sulfur dioxide, that actually offset some of the warming today and potentially in the future and introduce a large uncertainty both in our predictions and in our actual understanding of how sensitive the climate system is. Okay, so I'm going to go to this slide. I hope you can read it because it's kind of central to the talk. Mike Ralpick is a very creative scientist in Australia who wrote a paper that was one of the papers I read as I was preparing this work for Todd. And his work, perhaps more than anyone, really influenced my outlook on this problem. And this is kind of the key plot from his paper. And again, I hope the PDF is visible. But I'll try to guide you through it so that you can get the basic idea. Okay, on the x-axis, this is the cumulative emission of carbon since 1750. So everything is baseline to 1750, which is taken to be pre-industrial, just as I answered Phil's talk about temperature. The unit, yeah, all the units I'm going to use in this talk are petagrams of carbon, 10 to the 15 grams of carbon, or same thing as gigatons, which is 1 billion tons, metric tons of carbon. Policymakers tend to prefer million metric tons of CO2, but they just scale as 3.67. So if you don't like this, multiply by 3.67. This is the peak warming. Now keep in mind, this is not the warming instantaneously. It's the warming the Earth will achieve once it's come into equilibrium with this particular cumulative emission of carbon. Okay, so a series of very clever scientists, Miles Allen at Oxford, I can't remember his last name, Mr. Meinshausen, a young German scientist, Mike Ralpik, and some others, hit on this idea about 3 years ago that the best way to parameterize this question of global warming was in terms of cumulative emission of carbon. It turns out carbon stays in the climate system the way mercury accumulates in a fish. And as a result, the cumulative amount of carbon you emit, regardless of where it goes, and obviously some goes in the biosphere, some goes in the ocean, you're going to see that in a minute, it turns out the cumulative amount is proportional to the peak warming. And that vastly simplifies a really complex problem, right? Because you can just think of it as how much we've emitted. Now, Miles Allen put a website up when he discovered this back in, I don't know if he did it right away in 09, maybe 010. It's called trillionthton.org. I encourage you to check it out on your phone or computer. What it contains is a real-time estimate of the cumulative carbon. If you look at it, don't do it right now during my talk, you will see, actually, it's like you start looking, you can't stop. The numbers just change, in the 9th place or whatever it is. I just drove to work. There it goes, the 11th place of cumulative carbon. I checked it yesterday, and the emission was 562 petagrams of carbon as of October 16th, 2012. I think I rounded it slightly. That number might not mean a whole lot, but here's the key. It turns out a teraton of carbon gives you roughly a 2-degree warming. So we're 56% of the way there. We can't take that back, right? Unless some engineer, maybe one of you, comes up with a way of sucking the carbon out of the atmosphere, we can't remove that. That is there, whether it's in the ocean, whether it's in the atmosphere, whether it's in the biosphere. Now, these lines here are various ways of parameterizing the relationship between these two. The differences aren't important for the talk. These are some model runs, and the only point of the model runs, these are old SRES scenarios. The only points of the model runs is that they fall roughly along these various relationships. Okay, so you can see here's 1 teraton of carbon, or 1,000 petagrams or gigatons. If you come up to these lines, you can see it's roughly 2 degrees. You can see where are we in terms of commitment? Well, 562 puts us about 1.4 degrees. So, if the science behind this is right, and I think it is, we are committed to 1.4 degrees of warming relative to pre-industrial, regardless of what we do. If we all stop using fossil fuels today, we're committed to that. That would be the peak warming. Obviously, we've only experienced about 0.85 of that. Some of that is because of the aerosol FSAT. Some of it is because the climate system is slow. It takes several decades to come into equilibrium with a new forcing. Now, of course, the question is going to be how far along this curve are we going to move? And that's what I'm going to address next. But before I do that, I just want to point out this uncertainty band. So this is the confidence interval for these various predictions. And it's mostly driven by uncertainty in climate sensitivity, carbon cycle feedbacks, and aerosols. So even if we stopped emitting today, it's possible we could only experience a warming of about 0.8, roughly what we've had. And it's possible we could have a peak warming just short of 2 degrees. Now, that doesn't make me very happy because that uncertainty really makes guiding policymakers tough. But that's just the reality. We don't know the climate sensitivity of the Earth in aggregate, as well as these other factors, well enough to say any better than that, at least now. We've been working on that since 1979. So not me personally, but many very smart scientists. So it's not clear to me we're actually going to be able to do substantially better. Okay, so where is the actual, let's just talk briefly about emissions. Where are the emissions coming from? This is the latest update by the Netherlands Environmental Assessment Agency of emissions for 2011, going all the way back to 1990. The increase in 2011 was 3%. The share in 2011 was 29% from our friends in China, 16% from us. These are the two dominant emitters, but other developing countries, including India and other developing countries, are also major contributors. And And it's worth just reading out this statement. I'll read it from my computer. In 1990, the industrialized countries with a mitigation target under the Kyoto Protocol had a share of emissions of 68% versus 29% for developing countries. In 2011, the shares were 55% for developing countries and 41% for mature industrialized countries. It's easy to see why. The rapid increase is in China and India. The US and other industrialized countries such as Europe and Japan have actually been declining. This is one of the major reasons we didn't sign the Kyoto Protocol. And this is one of the major reasons that we won't renew, and we will not go in on an agreement to renew the Kyoto Protocol, because it makes a clear division between Annex 1 countries, developed countries, and Annex 2 countries, developing countries. If the major emissions are actually coming from those developed countries, they have to be included in any effective agreement. Just a couple quick other things on emissions. This is kind of a feel-good slide in case my talk is too much of a downer. US emissions actually have been dropping. In 2011, we dropped by about 3%. This is our actual aggregate emissions now in policymaker units, billions of metric tons of CO2. You can see lower. Part of this is the recession, but some of it is actual changes in efficiency in our economy, efficiency in our energy use, and also the widespread growing use of natural gas for electricity production. On August, just 2 months ago, the Energy Information Administration reported that US energy-related CO2 emissions in early 2012 were the lowest since 1992. So I think it's quite possible we will meet the president's target of a 17% reduction in 2020 relative to 2005. You could ask whether we have sufficient ambition in terms of how we're doing that, but for a combination of different circumstances, I think there's a pretty good likelihood we'll do that. That was our pledge. Okay, one other interesting thing about emissions, the data, you'll often hear when you go to talks that the US per capita emissions are 10, 20, 30 times the developing world. Folks are telling you that. They're not keeping up with the literature. It's not true. In fact, China has now risen to about 7 tons of CO2 per person. It is actually now on par with the European Union. The United States, yes, we're not quite the leader. This is the upper bound for all Annex 1 countries. I think Australia is the leader. But you can see we're dropping in per capita emissions, which is remarkable. And we are now within about a little bit more than a factor or 2 of China. So we're starting to be on a more level playing field in that regard. Okay, so that's really a whole separate talk, but it's just some interesting facts to think about in terms of the national, international diplomacy of emissions. So now let me get back to the question I raised 2 slides ago about what emission paths would actually take us to the 2-degree limit. So I'm going to show 2 slides like this, and they basically have the same form, and they're probably the central message of the talk. So I've got years from year 2000 to 2100 on the x-axis. And I have emissions, again, in scientific units, gigatons of carbon or petagrams of carbon on the y-axis. And in this first slide, I've plotted 3 different emission paths for the future and as well as historical data. So let me just start with the simple part, which is the historical data. So this is the emissions data updated to 2011. This is global emissions data. The average increase over the last decade is 2.7% per year. This is, and by the way, 2011 was 3%, so well, within that range. The green is what the International Energy Agency calls their current policy scenario. So this is basically an agency in Paris that looks at the pledges by various countries and well as their policies and makes predictions of what emissions will look like globally in the future. And their current policy's prediction is that emissions will rise at 1.3% per year based on current policies. In other words, assuming we don't do anything drastic in 2015 or 2020. And you can see that that requires a substantial reduction from the growth rates we've been experiencing over the last decade. But it still obviously puts us on a vastly increasing path. And the important point is that by the year 2046, on this path, we'll pass that 1 teraton limit. So again, the point is current policies would put us on a path to pass the 1 teraton limit in 2046. Now, I've added 2 other scenarios which represent ways we could get to the 2-degree limit. One is IEA's, what they call their 450 scenario. And that is basically a 450 ppm atmospheric CO2 level limit. And that's the red line. And then this is Mike Ralpick's 2-degree or 1 teraton scenario in blue. And in case you can't read these, the blue requires a reduction of 3.1% per year. And the red requires a reduction rate of 2.4% per year. You know, they're slightly different in the way they're parameterized, how quickly you turn around. The IEA wants to turn around more quickly. I like the Mike Ralpick's better because he says, you know, we're not going to turn around our whole energy infrastructure that rapidly. Okay, so a couple other quick points about this. The obvious one is there's a big difference between the green line and the red and blue line. You know, so in terms of ambition, if we're headed here, you know, that's the black, you know, we're pretty far from where we need to be. Now, if you look at various reports, such as the UNEP report and others, they'll talk about this thing called the emission gap in 2020, and they'll say, actually, this doesn't look that bad. But, you know, I think, you know, maybe 2020 doesn't look that bad, but as we look further out into this, we can see that there's a very, very big difference between what we would need to do and where we're headed. So the message here is that this is a tough, tough problem to do. Now, I also added, just for fun, on this slide, basically it shows the same material, same lines. I just added for fun that what it would take to get to a 1.5 degree limit. You would need a 15% reduction in emissions. Now, from everything I can understand in terms of reading literature about our energy infrastructure and the economics of that infrastructure, reducing emissions by 15% is impossible per year. It just cannot be done. My understanding is that the turnover time, realistic upper limit, is probably 3 to 4% in terms of replacing high carbon sources like a coal plant with low carbon sources such as a wind plant or a solar array. These numbers here are within the realm of possibility, the 3% per year, but they would require immediate and drastic changes in policy. Finally, this is a 3-degree limit, just for illustration to show that under 1% per year, that's probably something that is realistic. It's still very different than where we're headed, but I think that's quite doable, and that would put us on a path to about a 3-degree warming. And you know, that's my sense of my gut feeling tells me where we're likely headed and what is probably realistic. Okay, so let's see, I've got about 10 minutes. I want to just touch quickly on the question of carbon feedbacks. This is a really nice illustration from the Global Carbon Project of where emissions actually go. This was the decadal average for the aughts, about 8 petagrams from burning of fossil fuels, about 1 petagram from deforestation. This is how that is distributed. You might be surprised to learn that less than half stays in the atmosphere. The biosphere takes up about 1/4 of it. The oceans take up about 1/4 of it. It's important to understand that these ecosystem services are actually doing us a tremendous favor with one caveat. This uptake causes ocean acidification. But they are basically removing half the carbon we're adding to the atmosphere. If that carbon was all going into the atmosphere, the climate change part would be much worse. And I just wanted to briefly mention that there was a new work out in August, Ballantyne et al., out of the NOAA group in Colorado, in Boulder. And I'm not going to labor the details except to say that the actual sinks in the ocean, the sinks which are basically the ocean and the biosphere, which are shown in gray, as opposed to atmospheric accumulation, those sinks are increasing. There's been some crazy talk in the media about the ocean becoming saturated, no longer being able to take up CO2, the biosphere stopping. This is certainly not true. In fact, the biosphere is taking up a tremendous amount of carbon, and by all accounts, there's actually a greening going on which is believed to be a response to the higher CO2 in the atmosphere, which stimulates plant growth. So that is one piece of very good news in what in general is a really challenging issue. Okay, the issue of climate sensitivity is probably the most complex one, so I won't say a lot about it except to say it plays an outsized role in making these predictions. The current estimate of climate sensitivity for a doubling of CO2 from pre-industrial, which would be about 560 ppm, is about 2 degrees to 4.5 degrees. That's that factor of 2 estimate that created those big confidence limits in the slide I showed about 5 slides back. There's a wide range of estimates in the literature depending on the time period studied and approach. Tropical last glacial maximum SSTs based on newer methodologies require an equilibrium climate sensitivity of 3 Kelvin or more. This is work I've been directly involved in. And it's considered quite an important constraint on this number. So I don't think 2 degrees is going to be a number. We'd like it to be low, obviously. But I don't think we're going to get there. I think it's more likely to be close to the middle of that range. Okay, so I'll end my talk with just a few words about getting from science to policy. Before I went to Washington, I thought it was a linear relationship. Scientists speak, policymakers react. I couldn't have been more wrong. It doesn't work that way. It might work that way on a simple problem like this chemical is harmful to children and we want to take it out of a product, and the EPA responds accordingly. But when you get into something complex like global climate change, there are so many factors and so many constituencies and so many considerations that scientists can speak, but what's going to actually happen on the policy end is going to go through a very complex pathway. And actually it was very helpful for me to do that, to learn that, because I was frustrated when I went to DC. I was like, don't these guys get it? We're giving them all the information. And what I learned is it's actually, I hate to say this, but it's actually more the scientists who don't get it, because the policy side of this is so complex that, and admittedly, as a scientist, not many people are going to go spend a year, leave their lab and spend a year in DC to learn that. But for me, it was a valuable lesson. Okay, so what the science demands: a binding international agreement. All emissions would be subject to an agreement that all countries would have to follow. Not going to happen. It's not going to happen for a number of reasons, diplomatic. Probably the single most important has been what Roger Pielke Jr. has called the iron law of climate policy, and that is economic considerations are always going to trump anything else that we might consider, and we've seen that in this race for the president. A good way to think about this problem is ask yourself if you've ever heard the leader of a country or nation come out and say, I'm going to make a pitch for lower economic growth. That's the goal of my policies. Until that happens, I think a binding international agreement is unlikely. That's my opinion, but I think it's also the opinion of people who know better, such as Todd Stern. Okay, what is likely? National pledges, and I'm quoting directly from a speech Todd gave in Dartmouth College in August, in accordance with each nation's evolving circumstances, capabilities, and responsibilities. The idea behind this is something called pledge and review. Each nation, based on its capabilities, its individual economic factors, and so forth, pledges a certain amount of ambition. Nations compare those pledges and review them. The idea is kind of in the high court of opinion of between nations, countries will respond to those ambitions by raising theirs. Now, has it been proven to work? Not yet, but it's probably the way we're going. A second thing that's likely is no regrets action at the international and national level. I'll show you that in a minute. And lastly, there's a wild card, which is action at the subnational level, like California's AB 32, which is our Global Warming Solutions Act, I think it's called. It actually goes into effect, I believe, in 2013. There's an article about it in the Times this weekend. It's a little bit hard to know, how it's going to play out for one state to try to limit its emissions when other states within that nation aren't. But it's something to keep an eye on. And Charlie hosted a very interesting conference on AB 32 in the spring, which raised a lot of provocative issues on it. Okay, so very quickly at the end, I just want to just tell you about some recent no regrets actions, just an example of the kinds of positive things that are happening that can address this problem. First of all, the State Department announced in February 2012 the Climate and Clean Air Coalition to Reduce Short-Lived Climate Pollutants, which addresses what are called short-lived climate forcers. I haven't talked about these in this talk, but the idea is that a coalition of countries, among them the United States, Canada, Mexico, Sweden, will focus efforts on reducing black carbon, hydrofluorocarbons, and methanes. These are short-lived components of the atmosphere that have very high global warming potentials. And we can, by trimming them, we can actually trim the peak warming. So I think this is a really good idea. The International Maritime Organization reached an agreement last summer to increase the efficiency of engines in large ships used in international shipping by 30% by 2030. This is significant because 2.5% or so of global CO2 emissions come from maritime emissions. And it's, again, this is a no regrets action. A friend of mine at the State Department actually negotiated this agreement, and it was really fascinating hearing about kind of the diplomatic considerations that went into that. China was opposed to it, but in this case, other developing countries broke with China, and we actually were able to get that through. Last, the Reducing Emissions from Deforestation and Forest Degradation, the so-called RED program, has been put into place in developing countries. It's a 3-for-1 because it preserves forests. Preserving forests lowers CO2 emissions, increases the land carbon sink, and preserves valuable ecosystems. Again, I think it's a no-brainer that we should do this. And it's interesting to note that there's a 30% decrease in land use change emissions since the 1990s. And that's borne out by that new Ballantyne study. Okay, let me just throw up some conclusions. The 2-degree warming level remains a good measure of where risks start to accumulate. The threshold in cumulative carbon emissions for ocean acidification lies between 1 and 1.5 teratons, equivalent to 2 to 3 degrees of warming. It is no longer possible to limit warming to 1.5 degrees Celsius unless medium estimates of climate sensitivity are biased too high. In other words, climate sensitivity is lower than we think. Limiting warming to 2 degrees Celsius is unlikely without immediate and dramatic policy changes. There are some hopeful signs and recent initiatives, but their impact is not large enough to limit warming to 2 degrees by themselves. Thank you very much for your attention.
Part 2. How do climate scientists quantify temperature changes? And kind of the backdrop for this question is the British National Weather Service just came out with a press statement today saying that there has been no temperature increase in the past 15 years.
Okay, so let me take, those are interesting questions. Let me take them, they're very different, so I'll take them individually. You get a twofer. Okay, so the magnesium calcium, well, that's, I built that house. So basically there were, well, in the 90s we found that the magnesium calcium ratio of these little shells responds exponentially to the temperature in which they grow. And we were able to demonstrate that through culturing experiments we actually did out at Catalina Island, looking at plankton tow material, looking at different samples from the bottom of the seafloor. It turns out to be a thermodynamic response. You also can observe it in inorganic calcites. And the reason it works is that the magnesium to calcium ratio of seawater is constant. So as the shells grow, basically, that change is a specific response to temperature, not to the composition of the water. Your second question is a very interesting one. Fortunately, I read the blog, so I can answer it. There actually was no such report. There was an article in the British press which basically claimed what you just said, that there's been no temperature rise since 1997. It was in the Daily Mail, I believe, or one of those. What actually did happen is that the British, I think it's the, I'm trying to remember the name of it, I guess the Meteorological Service. The Met Office, thank you. The Met Office updated their temperature data, completed an update and refinement. And I've looked very carefully at this data because it came up at the State Department. And the basic bottom line is the question of a trend depends on your starting point. If you start in 1997, I didn't actually check, what this article claimed, but I'll take it at face value. If you look at from 1997, you might get no trend. If you look from 1999, there is a trend, and so forth. So it's very sensitive to your starting point. But nonetheless, it is correct that the rise in temperatures in the last decade has been much less than it was in the previous one. The previous one had averaged about 0.15 degrees per decade. The last decade, it's been at times close to 0, and maybe up to a tenth, depending on, again, where you choose that starting point. The standard answer as to why, and the Met Office actually put out a response, is that there's variability in climate, and it's not unusual to expect to have a period in which climate wouldn't warm. My personal response is it's good news. For whatever reason, whether it's aerosols, one argument is that the buildup of the economy in China has introduced more aerosols into the atmosphere, which are offsetting the greenhouse warming. Maybe there's, it could be due to natural variability. Whatever it is, it buys us some time.
So could it be part of that latent effect that you mentioned? It takes about 2 decades for today's CO2 presence to impact.
Again, we'd still expect, if there was no natural variability and the aerosols were not a factor, we'd still expect it to be rising because it would be responding to the rise 20 or 30 years before that. Yeah.
Just one last question. Was there any discussion at the political level of being proactive in mitigating response on the
So this is really not a question of reducing the input to the environment on the carbon side, but really either introducing into the environment things which change the response proactively, such as aerosols, such as creating seeding clouds, or even there have been wilder discussions of placing shields in orbit that are somewhat credible, at least on some sides. And so I was wondering if there's any discussion at that level of actually changing the models in an active way rather than just being passive.
Yeah, so Phil's question is about what's called geoengineering, which is the idea of, now that we've engineered a warmer climate, we'll engineer a cooler climate to get us out of this mess. Actually, when I wrote my application for the Jefferson Science Fellowship, that was the issue I said I wanted to work on. I thought it would be an interesting one from the issue of from the vantage point of international diplomacy. When I got to the State Department, what I discovered is that is an issue no one wants to touch. And the reason is there is this general sense, 193 countries in the room, the idea of trying to get everyone to agree as to when we should shoot up a rocket full of sulfur dioxide to cool off the climate, it's a really tough one. And I think the other factor is that when you look at the model simulations of what is going to happen, there's winners and losers. You get cooling, right? We know, for example, when Mount Pinatubo erupted in 1991, we got about, almost, I think, a degree of cooling in the year afterwards. But the problem is it was also the driest year on record. So you get this real patchiness in the distribution of where you get rainfall and where you get mostly less rainfall. Again, trying to imagine, we'd have to have this kind of climate czar for the globe, and it's pretty hard to imagine. I wouldn't say we shouldn't look at it. And this guy David Keith, I think he's at Harvard now. He spoke here at UCSB a few years ago. Has some really, really innovative ideas. This idea of levitating these magnetic balls that would actually deflect the sun's radiation. But I don't know. It's hard to imagine us going there.